In outbreaks, knowing the total number of cases is important. But sometimes, what really matters is speed. How fast is this epidemic accelerating right now? That's where the power rule comes in. The power rule is a shortcut in calculus. It tells us how to find the rate of change for any polynomial function in seconds. The power on t moves down in front of k and multiplies it. The original power on t decreases by 1. The derivative, or rate of change, is that's it. Move the power down, multiply for a new constant, then give t a new power of n minus 1. No simulations, no guesswork, just one quick calculation. Say confirmed cases follow this function. Using the power rule, the rate of change is. If we also check another time, say t equals 5 or t equals 6, we can compare those instantaneous rates. That lets us actually see whether the curve is rising faster at later times compared to t equals 4. That tells us the outbreak isn't just growing. It's increasing very fast. Just think about what is happening at t equals 4 compared to an earlier time, like t equals 1. Here's why the power rule matters. Speed, one calculation, instant insight. Interpretability, derivatives connect directly to real metrics, like cases per day. Precision, helps pinpoint when things peak or stabilize. Even a simple spreadsheet can handle this. With this tool, public health programs can move from passive monitoring to proactive response. If acceleration is high, resources can be shifted before hospitals are overwhelmed. That's math, turning into lives saved. So the next time you look at epidemic numbers, don't just ask, how many cases are there? Ask, how fast is this changing right now? Because with the power rule, rate of change is not a mystery. It's a calculation and a call to action. Keep in mind that the power rule for differentiation is one of many rules of differentiation. That's calculus for public health, fast, clear, and life-saving.